You've probably wondered how a machine, just a piece of code, can actually understand human language. I mean, how can it get a joke, write a poem, or translate things with such crazy accuracy? Well, the secret is a revolutionary idea, an architecture that totally changed the game. And to really get how brilliant it is, you first have to understand the huge problem it was built to solve.
So, just look at these two sentences. For any of us, it's a piece of cake. First sentence, it is obviously the chicken. Second sentence, it is the road. Simple, right? That's context. It's how we understand everything. But for a computer, this is an incredibly difficult problem. This exact kind of ambiguity is what stumped AI for decades. And to see how they finally cracked it, we need to look at why the old ways just weren't cutting it.
All right, so before we get to the big breakthrough, we got to take a quick look at the old approach. For the longest time, the idea was to make AI process language just like we thought we did, one word at a time. They were called Recurrent Neural Networks, or RNNs, and the basic idea was pretty straightforward. Read a sentence from left to right, one word after another, and just try to remember everything you've seen so far. Think about it like trying to read a whole novel through a tiny little peephole. You'd only see one word at a time, and you'd have to keep this running summary in your head of everything that came before. That's pretty much what an RNN was trying to do. And right there, you can see the problem. All the information has to get passed down this long, sequential chain, from one little step to the next. It creates a massive bottleneck. The model's understanding of a word way at the end of a sentence is completely dependent on this super fragile chain of memory that has to stretch all the way back to the very first word. And here's the kicker. What happens when that sentence gets really, really long? Well, the memory just fades. It disappears. This huge flaw even has a name, the vanishing gradient problem. The model literally forgets the beginning of the sentence by the time it gets to the end. So in our chicken example, if the paragraph was long enough, the AI would have absolutely no clue what it refers to, because the memory of the chicken or the road would have just vanished into thin air. So the whole field was kind of stuck. The models were slow to train because they were sequential, and they had this terrible long-term memory. Something totally new was needed. And then, in 2017, it arrived. It came in the form of one single game-changing research paper. And the title was just so perfect. Attention is all you need. It came from a team of researchers at Google, and it didn't just suggest a little improvement. No, it proposed throwing out the entire sequential RNN model completely. This was a totally new way of thinking. At the very heart of this paper was a powerful idea called self-attention. So instead of reading one word at a time, the model could now look at the entire sentence all at once. For every single word, it could figure out an attention score, basically how much it relates to every other word in the sentence. It could, in a flash, create this incredibly detailed map of how all the words connect to each other. Now, this is where it gets really cool because it completely solves our chicken and road problem. When the model looks at the word it, self-attention lets it scan the whole sentence and ask, okay, what's most relevant here for understanding it? When it sees the word tired, it gives a super high attention score to chicken. But in the other sentence with the word wide, it gives that high score to road. It's not relying on a fading memory anymore. It has a direct, instant connection to every single word. So this whole idea of self-attention is just brilliant, right? But how does this magic trick actually work? I mean, what's going on under the hood? What are the gears and levers that make this new machine, the transformer, actually tick? All right. Let's break it down. It really all comes down to this clever system that works kind of like a super fast library search. For any word you're looking at, let's call that your query, the model looks at all the other words in the sentence, which act like keys on a shelf. It checks how relevant each key is to your query, then it grabs the meaning, the value, from the most relevant words, mashes them all together, and creates a brand new, super context-rich understanding of that original word. So this query key value system is really the engine of the whole thing. But it's supported by a few other really clever components that make the entire transformer architecture go.
Let's just quickly run through the most important ones. Okay, so you're probably thinking, wait a minute. If the model looks at all the words at once, how on earth does it know the sentence order? I mean, the dog bites the man is very different from the man bites the dog. That is where positional encoding comes in. It's this awesome trick where a unique mathematical signature, basically a string of numbers called a vector, is added to each word. It's like stamping it with its exact address in the sentence.
And it gets even cooler. The next piece of the puzzle is called multi-head attention. The model doesn't just calculate these attention scores once, it does it a bunch of times, all in parallel, using different heads. The best way to think about it is like having a whole team of specialists all reading the same sentence at the same time. You know, one head might be an expert on grammar, another might focus on what the words actually mean, and a third might be a pro at tracking pronouns. You combine all their unique perspectives, and the model gets this incredibly rich, multi-layered understanding of the text.
Okay, one last little tweak, but this one was a huge deal. The original transformer design did a normalization step after all the attention calculations. That's called post-norm. But researchers found that if they just flipped it, doing the normalization beforehand in a method they called pre-norm, the whole training process became way more stable. And that seemingly small change was the absolute key to being able to build the gigantic, super powerful models that we have today. And gigantic is definitely the right word. The transformer wasn't just some dusty academic paper. It was the starting pistol for a complete explosion in AI that has totally reshaped, well, pretty much everything. Just look at how fast things took off. The pace is just wild. 2018, only a year after the paper, you get BERT and GPT-1. A year after that, GPT-2 is generating crazy realistic text. Then comes GPT-3 in 2020, showing what's possible at a massive scale, which led directly to the explosion of ChatGPT in 2022. This wasn't just slow progress, it was an exponential cascade, and it was all built on that transformer foundation. This is why your translation apps got so good, so fast, and why these creative AI tools are suddenly everywhere. So let's just put it all together, side by side. It's a night and day difference. Transformers took slow, one-at-a-time processing and made it fast in parallel. They swapped out a fragile short-term memory for a super robust system that is amazing with long-range connections. This is literally the difference between an AI that forgets what a paragraph is about and one that understands its entire meaning from start to finish. But you know, is it a perfect silver bullet? Not quite. All this incredible power definitely comes with its own set of challenges that are really important to know about. One of the biggest hurdles, as a user online smartly pointed out, is just the insane amount of data and computer power they need. Because the transformer is so flexible, it doesn't have a lot of built-in assumptions about language. That means it needs to see trillions of words to learn all the patterns from scratch, which makes training these things incredibly expensive and super energy intensive. And of course, you find other limitations. We were scouring the internet for all the deep, technical critiques, and, well, we found this one, and it certainly stands out. Now, while we can't officially confirm the threat from Megatron, it's probably good to be aware of all the potential risks out there. But jokes aside, the impact is just undeniable. The transformer gave machines a completely new sense, a feel for that complex, invisible web of connections that makes up language. It literally taught them how to pay attention. So the real question now is, since we've taught it to understand our words, what other complex systems should we ask it to understand next? You know, things like biology or finance, or maybe even the physical world itself.